one thing that you have to do before make any changes here is that you have to click Files and then save a copy in Drive. If you don't have the Google Colab account, I can give you like 5 minutes to make this account to follow this. I'm going to cover how to use the Google Colab in the form in the useful I'm just going to show how you use the Google Colab, and then there are some features that you need to know. So I'm going to cover that, and I'm going to explain how some of these the code structure is working, and what kind of library they're using, and show some fun demonstration about how things are assembled, and then we will have at the end we're going to have some image assembly at the end. Does everyone have a Google Colab account, or at least the people who wants to follow this?
I don't have one actually.
Yeah, I'll give you. So let's start. I'm gonna start this like at 6:40 like 3, so that you can have time to actually make this and follow this along. It's actually quite fun to use the Google Colab and see how things are all come together.
Okay, I've never been there, so I don't know how to make an account. Is it like?
Yes, yeah. Let's go over that.
Thank you.
Yeah, no problem. Let me log out from here. So there, you can go to the Google Colab, and then you can try to use your Google account here, and just log in.
All right, okay, nothing special.
Yeah, nothing special. Yeah.
Okay. Yeah, I think I'm already registered.
Yeah, that's good. Yeah, that's good.
Good. Yeah. Thanks.
Okay. So the can you access the link that I sent in the chat through your account?
Yeah.
Yeah. Okay. You're here. Then first thing that you have to do is that you have to do save a copy in Drive. So if you do that, it will make a copy of it, so that whatever you're changing here wouldn't change my code. Okay, so you can have your own notebook. So
all right. Okay.
Yeah. So now you have your own notebook. Then you can reconnect. Here on the corner, you can connect your internet to the Google's some remote location server, where there's a full of amazing GPUs and everything. And once you click this arrow button and then click the manage sessions, you can see what kind of a notebook is connected to the Google Colab. Okay, and if you go to the runtime here on this left corner, you can change runtime type here. So you should use almost always GPU. Okay, so select the GPU and make sure it is on GPU, because the GPU is really good at parallel computing. And I never use TPU, so it preset is a GPU. But if you pay extra $10, you can actually have a higher speed version of it. So if you care about that kind of stuff, you can pay $10 per month. But for now, we're okay with this, current version of the Google Colab. So I will hit save here, and One thing nice about this Google Colab is that it is a shareable code, and that anyone can run their uh, TensorFlow code, anything that's really heavy through the Google's server. And there is two tab buttons here. One is a code, one is text. When you hit code, there is a tab button here comes in, and you can code whatever you want. Like these are all in Python. For example, like something like this can happen here, okay? And then if you don't need it, you can delete these tab. And you can also add text, something like this. This is SDP workshop automated. Yeah. And these kind of comments help people understand or remind yourself what this code is made for. Okay, so here, so mathematically, if you remember I mean, not really mathematically, but if you remember my presentation, there was something called the PCA and then TSNE. TSNE is basically evolved version of a PCA. It is really good at showing the interrelationship between the one data set to another data set. And it is written by this guy, Lauren van der Metten, and he does a lot of research. He's actually a computational scientist, not like a designer or something. But then someone like people, this artwork is also made with the TSNE. I believe this was sold at insane amount of money for an NFT. Yeah, but anyways, but all it started with the scientific kind of research. How can you represent these complex multi-dimensional data set scattered into two-dimensional representation in the, let's say, more approachable way by a human being. So as you can see here, if you hit play here, it runs only this amount of a tab, okay? And then it is using the Skylearn data sets, which is the already available publicly. It is a kind of pre-trained data set, and then the import make Swiss roll is that with the data set, they're making this Swiss roll shape of a data distribution, and test to see how a CPA or TSNE is working according to represent the multi-dimensional data set into two-dimensional representation. Okay, and for any sort of let's say coding, you would think that you would write everything on your own, but then most of the time, especially as a designer, you would use a lot of other people's library. So if you go to GitHub or the OpenCV is a really good organization for any sort of image-based artificial intelligence. Object detect. They have an amazing object detection. The algorithm. It is all free, and then you can also learn more about their free courses. And there's also if you go to the TensorFlow. TensorFlow is Google's kind of let's say engine for the machine learning. So you can train large amount of data sets using their using your own computer or their server, for example, through the Google Colab, to learn how to, let's say, they categorize things or recognize something in the automized way. For example, this project here is that they're trying to, let's say, like recognize the handwriting with the machine vision, and then this is I believe this is like a kind of sorting the files into different categories based on the, I think that the image category, and this is a you're categorizing basically shoes to the coats and everything. So a lot of interesting things are happening in, on these organizations, and I would recommend watch some of the tutorials by the OpenCV if you're seriously interested in that, and also another. If you are interested in something like StyleGAN or a CycleGAN, this guy gives amazing tutorials of how you run the StyleGAN, how you set up everything, and theoretically what it means, all that. So this guy is also an amazing resource. So yeah, let's get back to the Google Colab. And here, like these are all just existing tools that's readily available on the let's say TensorFlow community, and these are just assigning the values for different color values for the Swiss roll. So if you can see here, it is kind of increasing from the red to the B. So the most of the machine learning operates on the RGB instead of the CMYK. So this is a kind of interpolating the data sets and then color code them with the RGB color code. So you have this Swiss roll here, and this is using the PCA. PCA is less of a, let's say, if you look at this kind of graph, main difference between the PCA and the TSNE is that the PCA is a linear dimensional reduction technique. So what they mean by linear is that this is a literal projection of what's happening in 3D. So a lot of the data that's behind one point to another point, it's hard to recognize a relationship between this thing to this thing. But the let's say if you run the TSNE is much the heavier of the heavier code algorithm, heavier algorithm. So it takes a while to run. But the thing about this is that it actually represents the data as a segregation instead of this like a literal representation. So this is a non-linear tool. The importance of this is that let's say let's look at the image like this, and then if you do PCA, you wouldn't have interesting kind of, let's say, boundary between like one thing to another. It will just literally be some sort of a grid condition where you have one similar thing to another thing. But then here there's interesting like insertion like this, like for example this brick facade. Brick facade has nothing to do with the glass facade, but then because there is this element kind of bridging the brick to the glass in terms of a color, in terms of a geometry, in terms of a materiality. So this happens in this area. But let's say if you do the PCA, it should be somewhere around here, right? Because this is a brick facade and this should all come around here. So like using the TSNE is showing something beyond our understanding as a visual kind of a representation, which is a pretty cool, I think. So that's why I think that I got interested into the TSNE first. Originally, what the people used for the TSNE was something like not this. So you see, like there is this like a weird symbols here, and then the people were trying to make the correlation between the one to another, between these symbols. Maybe some are from like ancient Greece, or maybe some are from like Egypt, but then what's the relationship between these two? And what is this? I guess I don't have that image, but then like here, like this is a much more diverse kind of the data set. This is most likely the text, but then text in a different background. But then you see some of the, like, you can guess some of the similarity between this style and then this style in terms of color, but then because the text style or some sort of compositional style is similar to maybe this one and that one, so it's like placed right next to it. So it's really like interesting to read on to this. Yeah, so and another thing about the TSNE is that there is a value called the perplexity. Perplexity is a value, more of a variable within the TSNE, the algorithm, and it is a kind of determining factor for how much of a force you're going to induce to the segregation of the data. So you can change those perplexity numbers, and here now we have a set perplexity of a 50, but then what happens if you put the perplexity of a 1? See, like now the it's if anyone is familiar with the thermodynamics, the perplexity is basically increasing the it's like a value for the increasing chaos or decreasing chaos. So this is like much more chaotic than actually how it was in let's say 50, because there is no segregation, there is no linearity between the alignment between the one data to another data. See, like this is now like segregated in different form, and this even if you run the same value, whenever you click run, it will come in different form, because it's a merely representation of the relationship between the one thing to another. So ideally, let's say we produce all these images for ourselves, and then we know what perplexity number works the best for the the segregation to your liking. Then you can keep clicking the button and then keep generating the different layout of a facade infinitely. So that's the power of the TSNE in, let's say, in relation to the designer's perspective.
So is it like more of a classifying method? It classifies the similar things and just arrange them together. It does not like create a new image of the facade.
Yes, it doesn't. Yeah, to do that, you need to do style again, which is another thing that I can cover in the future if you guys are interested. So if within the video, within this video, here this is using the style again. It creates literally an image of a new facade, let's say, or new street condition of a downtown LA. But our purpose is more, let's say, tamed down version, because you know how in style again there's always some weird geometry happening, but then my purpose was to create some geometry that makes sense for the construction, so that everything is in the kind of modular condition, but it is reflecting the context of a downtown LA through the lens of the TSNE. right? Like, because this is a more of a random iteration trying to make correlationship or to find some interesting features within the overlaid, a lot of the overlaid image on top of each other, right? If I, let's say, make a metaphor for the stallion, but TSNE is to make these with the existing image, like, you know for sure that this is like a glass facade, you know for sure that this is like a brick facade, then how can you make the, you know, relationship as an aesthetic between the brick facade to the glass facade? I think that is actually, in the meanwhile, this is looking very enticing. It could look very enticing. This is a more of a, I think, more close to the, let's say, practical method for that is for the construction. So that's why we're doing this. And it's how I was approaching, you know, my project in my perspective. Okay. And here we're importing another data sets. This is another example that is already has the classified kind of information array here. You don't need to know really like what's really exactly happening here. This is again PCA representation, and then this is a TSNE representation. Because there was no bias within this the Swiss roll the condition. It's like less biased. The categorization through the TSNE didn't work quite well, to be honest. But then if you have already some sort of a data set that's labeled under something, this creates actually quite accurate segregation of information based on the, you know, existing one compared to this one. This is showing just overlay of information that is on top of each other, so it's a little hard to read. And for this step, if you go to this drive, or if you just want to put your own images, you can put a zip file into your drive / my drive, and then this should be the name of your file. You got it? So if, let's say, I go to this, and then I'm just gonna save it again. Okay, download. And I'll just delete this again. And here, here you have this. And if you upload this to your drive, you can actually link your Google Drive to the Google Colab. Okay, so this is basically load. So drive.mount parentheses this /drive is basically linking your Google Drive into your Google Colab notebook. And this is just a comment. And the ZF stands for the zip file. If you use this zip file import, you can use a zip file. You can open the zip file in the Google Drive, so you don't have to always upload a large amount of the data. So that the by ZF, ZF and zip file, you're basically opening the zip file that is uploaded to your Google Drive, and I'm only just harvesting the number of the images that this file has, right? We just covered this in the Python when we were doing the cellular automata, which is the length of the file, and the length of the file means that the here, not the size of it, just the number of the images that's in there. Okay, so once we do that, permits this notebook to access to your Google Drive files. Yes, connect to Google Drive, and once you have this window, you can use your account and you know, just say allow then it will mount your Google Drive into the Google Colab. Okay. See, it tells you mounted drive, and then this is printed here, which is the number of the file. Number of the file in the zip file was 1,000, so that is accurate. And we're importing the image IO, and image IO is another library that is really useful for the like image, any sort of image applications. It reads image and it writes image. So it is a most common use, let's say, image manipulation tool in the Python, let's say. So you import their library. So whenever you see import, it's importing the public, let's say, library from this environment. Okay. And when you say from an import, that means that there is a large folder here, let's say something like A, and then there is a small folder here, something like B, and then you only want to import this. Then you say from A, import B. Okay, so that's what they're doing here. Yeah, and it's checking the image, and then it's making sure it is in RGB, and then it's making an image collection based on the number of the images that I have. So you see image collection here. You make the list of array here that is empty, and then through the for loop, which is until something happens, you still do it. So when f is in ZF file list, which was defined here, file list is the length, here, the 1,000. So f repeats for the 1,000 times, and then it adds individual images to the image collection here. And this is just to make sure that all the files are in the correct format. Does that make sense? Okay. And this is just checking the size of it. And when you do this, you can actually see what kind of images are inside, calling it out, like random images. So that you know what kind of images are inside. You can make the exact same process using your own images, okay? And once we do that, yeah, actually this doesn't matter. Actually this doesn't matter. So forget this, and this is just a checking your collection. Here, this is this is importing another the library from this Skylearn I mean sklearn. It's a community, and then they have the TSNE and then PCA as a code already. So we're just borrowing their library to use it to compare, PCA and the TSNE. We do what we're doing here is that we're making the images into, let's say, some sort of a array using the PCA. And then we're retrofitting the PCA data into the TSNE, because what happens if you just put a pure image into the TSNE is that it becomes like too heavy, or it could be it could not even run. So using the PCA, we process the image to make this tag image PCA. And if I go over like this part, there with the the harvested information or the number of the images that you uploaded, you measure in the length, which is 1,000, and then the image shape is the one thing that we measured on top. I think somewhere on top, and the through this you define x, and the within the I, you're repeating this process for 1,000 times, which is the image collection number of the image collections. And then with this predefined function, we're inputting the iterations, 1,000 iterations through this function. And then everything after everything is processed, you just get this PCA processed image. It's not important for designers, but if you're interested in coding and more of a serious computational design, I think that this sort of a problem, it's useful to know that this sort of a problem exists, and then sometimes designers need to hack the system really to retrofit these things, because ideally you don't actually want to go through PCA to do the TSNE, because these are very different algorithm. So if you process the PCA and then put it in the TSNE, then it will carry some of the biases that PCA already has, but it's fine for our purposes. And now, while I was talking about it, the TSNE is a process. Now we have a image TSNE as information. Through this process, we transform the image PCA to the image TSNE. So this library, the TSNE library, has this function called the TSNE fit transform, which you can transform the PCA data into the TSNE data. So that's done, right? And this is just the checking. Now we can make a TSNE image assembly here. You can define your width and height, and then the maximum distance, and this is the let's say distance between the one image to another image. You can actually change it to like different numbers to maybe not decimal. I think that I need to actually change another thing to change that. Well, I mean, in the version that we're going to write tomorrow, we're going to have some more flexibility in terms of how we make these changes. So, for example, if you don't want to have a grid assembly, what you can do is a half overlap, or you can do any number of overlaps, so that it creates a more of a interesting assemblies. Okay. So here, so like you can make your own, the NFT art using your own images through the TSNE and become a billionaire. And this was what I was talking about in the presentation for the text. Where is it? Oh yeah, this one. So so this is not my code. It's a code by Akim Ko, who is her GitHub user. It's I just scooped it out from the the GitHub repository. But what it does is that I mean, what's interesting about the TSNE is that if you have any sort of information, any sort of digital information, you based on certain like a file structure, let's say bias, you can make this as a vector information thing, you know, XYZ vector information. You know vector, right? So once that's happened, you can plot any sort of information into three-dimensional space. Actually, a lot of the machine learning is using this sort of technique. So, you know, have you guys heard of the Steigen latent spacewalk?
Yes.
Yeah, if this is XYZ, what the latent spacewalk is doing is that selecting a point here, like you in the latent spacewalk, you predefine a seed, right? Let's say this is a seed A, and then let's say this is a seed B, and latent space is basically going through this like multi-dimensional space in some sort of a spiral to get to from point A to point B. So, but instead of making the connection from A to B, what the like let's say TSNE does is that they use the vectorize the information as a coordinates to make the to measure the affinity towards one to another, so that they can represent in the, let's say like this is some sort of a like plan view of this thing. They, instead of just projecting this coordinates right on the canvas, what they're doing is based on this measured distance from the one to another, and then another thing to another thing, they measure the distance so that the, let's say point A and then the point B, how much of a distance does it have, and then where is it going to locate? Is it going to locate here? Is it going to locate here? But this B has another relationship with let's say C here. But then like is C close to both A and B? If that is the case, C will locate here, right? So that's the kind of you know the science behind it. So let's say we do this the text one.
So, but a latent walk is not PCA, right?
It's not. But I'm just making like a, let's say, metaphor, because the latent space walk also has a vectorized the space, right?
Mm.
And if you're familiar with the latent space, you can like pick a seed, and then you can like set some sort of parameter to tell the latent space walk how to walk, right? Where to walk, you know. So that's but then in our head, you would think that in the vicinity of this point A, something that looks very similar would be here. But then in reality, in the Steigen, because it doesn't really care much about the relationship, it only cares about the features. So the point C and the point A could completely look different from one to another in terms of image. So that's why the Steigen latent spacewalk is very interesting when you run it, because you encounter all these like a weird correlation from one to another in the way that human cannot completely understand how it's going, but then it seems like it's transforming to one thing to another. Yeah.
Right.
Okay. So so if you have your own, I don't know, diary or some sort of a text, TXT file that's stored in your computer, I would recommend you try this, because it's very funny, you know, because it finds a correlation between the one text information to another text information in a very interesting way. But you know, so this is you can basically here you can these are just for the library that's necessary for this to run, and you can basically download or link the text information into here, and this is a this is like, let's say, variable, right? To load that variable, you can you have to define the URL, and then URL is in it. But then at the same time, alternatively, you can also do this. But then, just for the sake of clarity, people like to use this this form, right? And you know, this isn't that important, and it's this is basically they're deleting all the unnecessary information. They just want to harvest the text. So through these processes, you're deleting all the unnecessary information, and then just left with the pure text. If you run this, and let's keep running. This is just downloading some already like a trained data sets from the elsewhere. And this is where you're vectorizing the text. So here, you see this word to vec. This is another very useful information that you can have. So, or the, let's say, library you can have. So what's interesting about this is that because the latent space is working in the vector space, you can basically choreograph your styling and latent space based on your diary. So if you have like some sentence like I don't know, like, I ate ramen today, like this, then you can actually put this into the word to vec, and then use that vector as the making the orientation from the one point to another point. So that's also quite interesting tool. You can do the same with the music too. If you have your favorite music, you can do, you know, Stygian interpolations with the music too.
Can I just quickly ask if so is that related to what's called VQGAN?
Yes, but it's not like exactly the same. VQGAN is a more heavily, like, you know, influenced by the word itself. But then what I was describing was more of a how you travel from one space to another space. VQGAN is basically you're training machine learning agents to create certain images. So let's say if you say like a column, it has some understanding of what column is, and then it will generate the column as an image. That's the VQGAN. But what I was describing was that you're only choreographing the latent spacewalk from the A to B.
I see. Okay. Yeah. Sure.
Yeah.
Makes sense. Okay.
Okay. Okay. No, I don't need that. See, like here, for the TSN, you can choose a different perplexity, so that it aggregates in a different way with the different degrees of a chaos factor. But yeah, here look at some of the relationship between the one to another. You know, like within soul, rage, agony, monster, like these are like similar kind of word. And Frankenstein is quite close to the monster, and yeah, like lovely, beautiful is just linked to the somehow appearance. So like these information, something that we cannot easily make a link between the one thing to another is much easier to be expressed through the TSNE. That is the power of the TSNE. I just wanted to quickly go through how the process works, and then tomorrow I'm going to have more about the new collab, the notebook, so that with the most updated version, like like I have this like Python code, but then I just have to put it in the Google Colab. But yeah, anyway, if I show you guys what we're gonna do tomorrow, just for a moment, and then in terms of a demonstration, I wanna show you guys how this works. So and here, so these are all the libraries that I'm using, but I'm going to hide that for now. And then here, these are the important variables that we can change in the code. So you have to. So the reason why I was working on that processing code earlier, and then tell you guys to make the 512 by 512 images, is that I designed the code to work in the this dimension. You can always change this to different number, like for example 256 or 1024. But for the purposes of a more of a unified kind of instruction, and I wanted to use a 512. Some of the images that I use to create this the image assembly is on the Google Drive, the Google Drive. So if you are wondering the standard for the what kind of images do you need to prepare, it is up there already. And here, you're defining your title of the image. It only output as a JPG for some reason. I don't understand why, but it's just how it is for now. And you can name whatever you want, but don't put dash or space. The golden rule for any sort of programming is that the camel case. So, whenever you need the the spacing, you just need to capitalize it or put the underscore. You don't want to put the space here, because for some the computer language, space means actually some function if it is within the certain condition. So don't do that. And this is the perplexity. So 50 is usually how I found it as a most well organized within having the good enough of a dynamism. So I keep it in that. And then this is a number of iteration for the TSNE algorithm. I put it on a very, very high number, but if you're not patient, you can put it on the lower iteration. Then larger the number, usually the better for this sort of application. And another thing that I changed here was, okay, here. So here, if you change this number, you can change the overlap space between the one image and the space. I'm just going to change it back to how it was. And Here, I just made it as just like a command note. So whenever I run it, I don't have to do it again. But you see, there are some variables that you recognize here. This is a direction, and then this Python is referring to the name of the file here. So once you type the Python and then the space, and then put the name of your code file, it initiates that the file within this Anaconda prompt. And the direction is defining the direction of your current images, and the size is also quite important. So if you go to this like temperature and then everything else. Okay, so I'm in this folder, and do you see the number of the images down there is a 1698 and the 1698. So you have to think about how many square spaces will you fit it, right? Will you fit? So this XY should be the same. So it could be 30, it could be 30, 30, it could be 40, 40, but then you have to remind yourself that the multiply over X and Y cannot exceed the total number of images. So your grid size is defined by the total image. So right now I have a 1695. So I will put 1695 here, and you can just square root, and that will approximately output 41. Yeah, you can put one number lower. You always cut these decimal number out, and then input this as a size, because there's no such thing as a 41.1 grid. So this is how it should be. And when you run this, actually, I think my graphics card is fighting the Zoom and this priority between this program and the Zoom. Yeah, because if there is too much of a, let's say, graphic cards load from your computer, this doesn't run. So how can I show you guys this how it's running? I probably have to stop the Zoom to make it work. But I already have all the outcome. So this is a result. So the note that the number here it refers to the perplexity. So perplexity 1, 5, 10, 12, 20, 50, and 100, and that this is iteration number. Okay, and this is a much more scattered, because the degree of a chaos here is much greater than here. Perplexity number was lower on that, and the perplexity number here is larger here, and you can see how this let's say the segregation increases with the perplexity increasing, but then beyond 50, like when it comes to 100, it becomes more of a, like, let's say, circular kind of segregation. So if you were imagining those dotted version of the segregation, if you increase the segregation or the perplexity, you would have these chunks. But if, let's say, within the 50, it's a little more blobby, like this. So it creates the interesting. And this, for me, this is more interesting than this. So yeah, this is what we're gonna do tomorrow. Sorry for the processing not working, and the image cutting not working. I will look into this issue tonight, and then I will send it by end of today, or by midnight, so that you guys can use it if you want to use it. But if you don't want to use it, I already have here under the images, facade clip out all. Everything is already cut to the size that we are going to use. This veggies, yeah, so don't worry about it if you're busy. You can just use this data set to run the code tomorrow. And tomorrow will be mainly, going over how to make the TSNE through the Google Colab. If anyone's interested in installing this Anaconda environment in their PC, let me know. Shoot me an email if you have a problem with the installation. It is very important to install things on the exact location and then follow the exact the instruction as I was putting it in. Oh, now it's warning. Oh.
Those about 500 images that you have in that data set, do they all come from one image, or you use several to get
several? So if I show you my but like you can just, it doesn't have to be all architecture. If you're not interested in making architectural facade, it could be something interesting geometry, and it will still make very interesting, let's say, assembly. So if you don't care about that, just download a few images from your personal phone and go from there. If you don't want to take a lot of images, it takes a while, yeah, so I took a bunch of images that, like this, like this. I have a lot of images, and then I cut it using the processing code, and sometimes use Photoshop to create. Yeah, and it doesn't have to be skyscraper. You can do suburban architecture too. It will be actually more interesting to include these different types of a neighborhood. For example, Paris has a very specific types of architecture around all around their town, and I'm pretty sure Tehran, it will be completely different from let's say London, and Seoul is completely different from like LA. All this type of things. I think that is better, and at the end I can combine all of your images into one giant assemblies, with my the images, so that you can we can all keep that as a the souvenir for the class. Is there any questions during for today? And the assignment for tomorrow is that review how to use the Colab, and if you don't have account, make it, and get familiarize yourself with the Python and the Java just a little bit more, so that tomorrow when I'm doing more like a fast paced, like a difficult, coding stuff, you can at least understand what I'm trying to do. So yeah, those things are those 3 things are mainly the assignment for tomorrow. But is there anything unclear about the directions, or any questions in general, or any other questions regarding to the machine learning or AI stuff? Like if I can answer that, if I can answer, I will answer.
I just wonder if you're going to send the recordings directly after the end of this session.
I think that's a more question for Hanjun and Sumin. I'm sure they will send you, but I don't know when exactly. Hanjun, are you here? Maybe he's not here. But I will get back to you, check with Hanjun, and then send you email if it's going to send out today.
Yeah, because I mean, it's probably good to review things if we don't understand something, or to get back to the video. Nice, thanks.
Okay.
Actually, I have a question.
Yeah.
Okay, so as for the perplexity, so let's say if I set the number 50 for perplexity, so when I just run that algorithm, can I get the every time same shape, same graphic, or no? Okay.
Yeah.
So
yeah, I know that it's a little annoying, but it's your luck basically to get the beautiful image. But within the same perplexity, more or less, it will give you similar effect. So yeah.
Okay, so sounds like basically that whatever number perplexity put in there, basically that show a lot of, let's say, pattern combination of the images. Is that
more of a behavior pattern between the one image to another image? Like how do they relate to one to another? A and B. That sort of a thing. And how much of aggregation is it going to have? As I showed you with the 100 perplexity, it was much more compact like this, and then with 50, it was more like a little bit blobby, a little bit more freeform, as an image correlation. So these are the repeated this effects you can reproduce, but then whenever you run new TSNE, it's always trying to just create the 2D representation of the current status. It's like, I guess, like, it's probably wrong metaphor, but then it's like what is it, in terms of the physics, it's a quantum dynamics kind of a situation.
Yeah, I see what you mean. Yeah, okay.
Yeah.
I'm just curious, is there a way to find that relationship as well between each different outcomes as well? Like, even if I say, even though I set the same perplexity 50, let's say, but when as much as I run the algorithm, it shows different outcomes. So my question is there any other different algorithm to find that the relationship of each different outcomes?
So what we can do is that it will not be super scientific, but then we can write processing code to analyze one image to another image, like what's the difference based on the color value of that the each module. So
Gotcha.
Yeah,
because let's say I got the one image on the grid, let's say that is the image was placed on 5 by 5, that location there. And next time it shows that 5 to 6, and the other one is 6 at 5, something like that. So maybe we can guess kind of some group or another area for the images where the image is located. So maybe that was just my 2 cents on that. But okay, thank you.
Yeah, no problem. Anyone else?
I don't know, maybe this is like not related to the TSNE thing, but I'm interested in the point net
.NET.
for semantic segmentation. Like it's more for point clouds. I don't, do you know anything about that? I don't know. Just like to.
Yeah, I don't know much about it, but you know, I will look into this tonight. And, let's see.
I
Yeah.
actually found like a very nice research paper about that. But I mean, I can share it if.
Oh, this is interesting. Yeah. Okay. Yeah. Oh, it is like more of a targeted segmentation based on the point cloud.
Exactly.
Oh wow. Okay. Yeah.
I have actually 3 things in here, maybe. Yeah. Or 2, maybe. Okay. It's like 2 research papers, but yeah.
Yeah, this is super cool.
Because there is this 3D GANs, right? But I've heard that it's very heavy.
It's very, very heavy and it doesn't work very well. Yeah.
Yeah.
Initially, what I wanted to do was something that's more similar to the 3D GAN, but then I turned to more of a 2.5D application. Like I make the image first and then make the interpolation of the 3D from the 2D image. The reason why I turned to that direction was that I couldn't find any like reliable 3D GAN that can be effective and then pretty at the end. So I wanted to have more control on my hand using Houdini rather than the fully automated kind of the machine learning process. And yeah, but a lot of people are researching for the 3D GAN, and a lot of large, as long as I know, a lot of like a big architecture firms also interested in this like a 3D GAN idea. So like, yeah, a lot of big companies are doing this sort of research.
Because I thought that maybe this approach, I don't know, maybe it could be like an alternative for 3D GANs, like to deal with point clouds rather than, I don't know if it's right what I'm thinking. I know it's logical, but.
Yeah, yeah. I mean, I have the Houdini version as my final, but then I also did the depth analysis algorithm on the facade images, and then made that as a point cloud, and then make the point cloud assemblies in the processing before. So if that's something that is commonly interested by the class, I can try to add that at least some of the components into the tutorial for either tomorrow or Sunday.
Yeah, cool.
Yeah.
Awesome. Thank you.
Yeah, thank you. So we ended a little bit early today because of my problem with the processing, but it's okay. I'll make it up to you guys tomorrow. Okay.